So I will talk about unlocking practical quantum advantage with near-term quantum computers, and I will make some bold claims, so I'm happy to discuss them to keep alive, let's say, this conversation. I will say that in order to do so, one of the possible ways is to change the way we measure. In particular, I will claim that quantum advantage in near-term quantum computers can be achieved if we use informationally complete generalized measurements on near-term devices, and I will define them soon. So I'm claiming we don't need to wait all the way till fault tolerance. Of course, everyone wants to go towards fault tolerance, but it is possible to have useful and practical quantum advantage before. That will be my main claim. The talk is divided in 3 parts. I will begin by presenting what adaptive, informationally complete, generalized measurements are and how to implement them in realistic devices. Then I will describe a practical hybrid chemistry algorithm for ground state estimation, and this is very much related to what Sophia has been talking at the end of her previous talk. And finally, I will present a practical error mitigation method. Here with practical, I mean that these things don't work just with 5 qubits or 10 qubits, but I'm interested in the regime of 50 to 60 qubits. So that's the goal. And the team behind this is actually my startup team, the Algorithmiq team. You see them in the natural environment in Saunasaari in Finland. Saunasaari is the island of sauna. It's an island where there is only a sauna, and the sauna is behind us, indeed. Now, again, let me go back to this point. Knowing how to extract information on a quantum computer or any quantum device is key to unlock its power. What do I mean with this? What I mean is related to what is known as the measurement problem, which is actually quite different with respect to the quantum measurement problem, quantum to classical transition, that I've been used to work for many, many years. So it's a different, much more practical problem. And specifically, it's related to many interacting electrons. And this is related to this fact. Take any operator O, you can write it as the linear combination of Pauli string pKs. These pKs are just product of single qubit Pauli's operators. Okay? This is a general decomposition. Now, for many problems, for example, chemistry, Hamiltonian problems, the terms in the sum are of the order of n to the 4th, where n is the number of qubits. Like in full generality, this would be 4 to the n, right? But you're sort of lucky. You have only n to the 4 terms, but it turns out that this is already quite a lot if you want to be very precise in the estimation of the mean value, and in particular, the error is given by this formula, where Sk is the number of shots you need to estimate accurately each Pauli term. And when you do quantum chemistry simulation, you really need a very, very, very good high accuracy. So epsilon has to be very, very small. And the problem is that you want to know how S, the total number of shots, scales with n, with the number of qubits, to achieve a sufficiently low error. For example, in chemistry, so-called chemical precision. Now, the answer to this question is bad. I mean, it really scales badly. We know that this is one of the main problems of near-term algorithms. It scales as something like n to the 5 or n to the 6th. So if you have 100 qubits, this is an impossible number of measurements that you have to do to estimate just one mean value, okay? So this is very limiting for near-term devices. However, one may argue that not all measurements are equal, and you can imagine that you could change on the fly the measurement in order to minimize the error you are obtaining, the statistical error in this case. And this is actually something that we have been proving and publishing last year. The person behind really this idea is our chief scientific officer, Guillermo Garcia Perez, also a postdoc at the University of Helsinki. And this was a collaboration with a group of Ivano Tavernelli at IBM Zurich. Now, what is the key idea behind this adaptive strategy? So you want to estimate the ground state energy of a molecule. Now, you begin by performing a small number, S prime, of measurements with a given measure, P of M's. I will define soon this measurement, M. This star can be small. It doesn't have to be very, very high. Then you look into the neighborhood of M, and you search for other measurements which lead to a smaller error. You select the one that has the minimum error, and you implement only that on the quantum computer. And then you repeat. Okay? So it's an adaptive strategy that searches the minimal P of M. Now, why this requires informational completeness? Why do I need an extra step? And it doesn't work with any measurement. Because in order to calculate, to look in the neighborhood of M, I need to use the previous data and to be able to calculate now the error, so, which is another operator, right? Now, how do we solve this by using informationally complete P of M's? I have to first describe what they are, and I will introduce single qubit informationally complete P of M's. They are 4 linearly independent positive operators. I will call them pi I. They are positive, they sum to identity, and they span the whole space of operators in the Hilbert space of the qubit. Of course, by definition, the probability of obtaining outcome I is just given by the trace of rho pi I. Okay? Generally, one of the ways of implementing each of these P of M's is by using an additional ancilla. So if this is the density operator of the qubit, I need an ancilla in the ground state. I need to implement a certain parameterized unitary, 2-qubit unitary, and then I measure in the computational basis both the qubit and the ancilla. I will have 0, 0, 0, 1, 1, 0, 1, 1, and this corresponds to the outcome of the 4 P of M's. Okay? Now, the interesting thing of this approach is that you can write any observables in the basis of the P of M, okay? This is just a decomposition that I wrote before, and then the mean value of the observable will be just given by certain coefficients omega m and probabilities to obtain outcome m. This entails the possibility of using Monte Carlo integral to estimate the mean value of the observable, okay? So I make measurement and I'm sampling the probability distribution. I calculate classically these coefficients and I estimate with an error that I know the mean value of the observable. Now, this is one example of how this works. Here we are calculating the ground state of a 12-qubit lithium hydrate. This is again the VQE example that was introduced before by Sophia. Here is the error as a function of the number of measurement shots. And you see the chemical precision line here for this example. And now the red line corresponds to the adaptive strategy, which of course beats the 1 over square root of s statistical error behavior because we keep adapting, okay? And we reach before, compared to other methods, the chemical precision. When we look at the scaling, this is the number of measurement shots needed to reach a certain values of epsilon. For example, 0.5 millihartree here has been chosen, which is not relevant. I can choose another value here, as a function of the number of qubits. Now I look at the hydrogen chain because I need to grow the number of qubits, right? And the scaling that we obtain is of the order proportional to n to the cube. This was in this paper, while more naive methods have n to the 6th. Now, recent results have n to the, show that we can go below n to the 3. So we think that our limit is n to the 2nd, and I can explain why this can be done. But this is a sensible reduction in the scaling. Now, how can we implement this method in practice in experiments? There are 2 limitations. The first one is the number of qubits, because we need to double them. And the second is that, in fact, we have noise, that the P of M's, the detectors, are not ideal. They have errors. The solution to this is contained in this preprint that recently we put in the archive. Again, the main idea is from Guille. The coordination was from Zoltan Zimboras. And the main people who worked on this are Adam Gloss and Anton Nukanen. So the idea is the following. Let's begin first with a single qubit implementation of the P of M. and then with an error mitigation strategy that allows to take into account the realistic devices. Now, you may think that actually doubling the number of qubits is not so bad, but as a matter of fact, if you look at the connectivity of the device, very often you don't have a free ancilla for each qubit, especially because you are at the result of a certain computation of a certain circuit. How can we go beyond this? Well, there are other ways of implementing POVMs, and in particular, there is a class of POVMs known as PM simulable POVMs, a subset of which is informationally complete. The ingredients to implement this are the following. I need K projective measurements, I need a K outcome probability distribution, and I need a set of conditional probability distributions. So these are the ingredients. I will show you how to do it given these ingredients. Now the recipe, yes. For a single qubit, of course, the tensor product of informationally complete POVMs on each qubit is itself an informationally complete POVM for the n qubits. So I begin by sampling a value of k with probability alpha k. Subsequently, I implement the projective measurement as a unitary on each qubit, uk, followed by a measurement in the computational basis. And now I draw a value of m, and here I consider the probability of obtaining m given k and b, which were fixed in the previous results. And I use this to relabel the outcomes. And in the end, I have to check that what I implemented is informationally complete and in fact implemented in the device. Now, the reward of this procedure is a class of n-qubit informationally complete POVMs, which are parameterized with parameters 5 that come from the unitary for the probability distribution and from the conditional probability distribution. And I can use them to do precisely the same thing that I did before, these adaptive strategies. And here you see the green line is the dilation-free, so the single qubit POVM, while the pink line is the dilation POVM. Both work in beating the 1 over square root of s. One is better than the other. Now, just incidentally, because many times this is, people ask me about shadow tomography. If you know shadow tomography, this is similar to shadow tomography. Shadow tomography corresponds to one precise value of alpha. So it's one specific example of this, corresponds to alpha equal 1/3 and a specific unitary. So we are talking about a much wider class, which we need in order to successfully adaptively improve the measurement. Okay. Now, second problem, the readout and gate noise error. And here the problem is that we need to correct the empirical distribution of outcomes by modeling the measurement error. The reason, it will be clear in a moment, but of course what we need to do this is use quantum detector tomography, which is generally used in experiments with quantum devices. And obviously the problem is that the estimation of the mean value will be always biased because the actual probability distribution of outcome is affected by noise. So I'm calculating it using the ideal one, using the ideal POVMs, but in fact, I will have a biased value because what I'm implementing are not the ideal POVMs, but the real ones. The solution is simple. I need to actually approximate and actually use the POVMs which I implement, and to do so, I use quantum detector tomography. So we use quantum detector tomography to estimate the real implemented POVMs, and then we expand the coefficients, the expectation value of the observable as a function of what are the real POVMs. Now, this may seem to solve completely the problem. However, there is an additional problem. This, unfortunately, does not work if you have an adaptive strategy. Because the adaptive strategy requires parameters and requires to guess, or actually to calculate, POVMs in the neighborhood of your initial one, okay? So you need to be able to do so, to construct a classical model that associates realistic POVM effects to the value of the POVM's parameters. So you need to have really a model which contains parameters to use in order to make this work and to solve the bias. And this is actually what we do by characterizing each element in the physical implementation of the generalized measurement. So what you need to do, you have to use quantum detector tomography for the projective measurement in the computational basis, and then you need to characterize the C0, well, they are parameter-free gates, so you have to do quantum state tomography, and for the single qubit rotations, you have to model the actual channel, okay, and use it, and finally, you have to model also the ancilla doing quantum state tomography. So you build a model of your P of M, and you use it in the adaptive strategy. This gives you the correct values, or the as close as possible correct values of the probabilities Pi, and also a model of parametric informationally complete POVMs that you can use to incorporate noise and imperfections. And this is how it works. Again, these are examples. We have tested it on many different types of molecules and many methods. But here you see the blue line show this bias that you have if you don't do any tomography, while the green line show you the adaptive strategy with quantum detector tomography, and here we use IBM Hanoi noisy quantum computer models for doing this example. So this solves two problems for the implementation, and this is somehow motivates me to think that these type of measurements are actually implementable today on near-term quantum computers. Now, what are the benefits of using them? Well, the first thing is that, of course, they are scalable. I can do it for n qubits. But most of all, they enable a number of methods and algorithms that otherwise would have a too large overhead. Okay? And in particular, this is due to the fact that I can use the same data to estimate mean values of other observables. Of course, there is a caveat. I have to do it in a way that with a sufficiently appropriate variance, okay? But I will discuss this later. So this can be done. So you have, for free, the mean value of a large class of relevant other observables. That's the claim. So and now I will briefly talk about one application that is doing chemistry on near-term quantum computers. And I don't have to say many things because this was actually very nicely explained by Sophia. What you do in this case is really you want to encode the state of the molecule in the quantum device. Your goal is to find the state that minimizes the energies. And you do it, of course, with this hybrid approach. You need to measure the energy and iterate. And so I will be very brief because, again, this was nicely described before. Now, there are a number of challenges with this approach. First of all, the measurement problem I discussed before. Okay? Second, the Hilbert space is a very large space. When we create these ansatz, this is absolutely not easy, especially then to converge towards the ground state. The noise biases the results. I only consider the noise of the errors, but of course there are noises everywhere in the circuit. And qubits are a scarce resource. So how do we assess all these problems? Well, I hope that I've convinced you that this is a very good strategy for the first method, because it gives a very nice scaling. Let me tell you about the ansatz. Again, I don't have to elaborate more because this was mentioned before. I think it was the first type of ansatz, or one of the first type of ansatz that was proposed is chemistry inspired. The advantage is that it really captures some elements of the ground state. The disadvantage is that unrealistically long circuit depths. Then we have hardware efficient ansatz, which is implementable. It takes into account the hardware constraint, but it suffers of barren plateau, expressibility problems, so it is also very limited. And the most promising strategy is the strategy that was devised by Sophia and her team, that is AdaptVQE, or the variant of qubit AdaptVQE, which is chemically motivated, and then this really nice approach that gradually grows the circuits. Okay, so it's really combined the advantages on both, but however, it is very intensive in terms of number of measurements that you need to do, because you have to measure many observables in the pool. And I will describe an algorithm that we are proposing now to solve this, or to mitigate this problem, okay? So the first thing I have to say is that what you need to do when you want to simulate a quantum chemical problem is that you have to fix your basis set. This fixes the number of spin orbitals, and therefore it fixes the Hamiltonian. Initially, what people did was they had, say, 10 qubits, then they fixed the number of basis set to handle 10 qubits, and this means basically that what they are known as the core spin orbitals were frozen, and these 10 qubits described all the rest, okay? And they used these on the quantum computer to do VQE. However, a much better approach is what chemists do normally, is actually to use a very large number of basis sets, because remember, the actual ground state is obtained only in the infinite limit of the infinite basis set. So actually what chemists do is that they use a very, very large basis set, but they choose a part of it to describe the active space. This is the CAS method, okay? So only this part is measured on the quantum computer with a VQE. And in a way, a rough way of saying is that treating a properly chosen subset of spin orbitals from a large basis set is often better than using a very small basis set. This, again, is what chemists do normally. Here, I indicate with CAS 2 in this example, just because CAS is this method and 2 is the number of electrons, while the other 2 is also the number of orbitals. In general, these are called CAS MN. So this is one step of the procedure. Additionally, we do something else in a method that we call VQE SCF. So this is an additional implementation or activation that comes from another classical chemistry method, CAS-SCF, which we now integrate with VQE. So not only we consider an active space, but also we optimize the orbitals on the go. So we rotate the orbitals as we grow the ansatz, okay? So while growing the ansatz of the adaptive VQE, we optimize the molecular orbitals. This is a typical self-consistent method that chemists do. So we combine these two techniques. And now this is the plot that I want to show you. This manuscript is in preparation. Here, the main idea came from the discussion between Guy and our lead chemist, Stefan Knet, and the main people implementing are Aaron Fitzgerald and Anton Buchanan again. So here I'm comparing 3 curves. Okay, this is chemical precision. This is lithium hydrate with a CAS4, and this error is the error with respect to the ground state of the CAS-SCF, okay? And here I have number of CNOTs, okay? Now, if I do UCCST, so if I don't do any CAS, if I just do what I said initially people have been doing, which is also grows a very large ansatz, I obtain a point which is bounded by this value, because I can never go below this value in the estimation of the error. If I use a CAS, and here we use a qubit adaptive VQE, mind the scale is not very clear, because actually there is a small reduction as we increase the number of CNOTs, of course, but it reaches the bound of CAS, so the minimum energy of the CAS is immediately reached here. But if we keep, while we grow the ansatz, and the grow the ansatz you see here, increasing the number of CNOTs, optimizing for the spin orbital, we go all the way down until the real minimum value of the CAS-SCF, okay? Now, this is nice, but this is still 8 qubits, right? I was talking about something which is scalable. How can we scale it? The idea of scaling comes from the use of informationally complete data, and is due to the fact that I can use in adapt VQE to calculate the pool of operators and their mean values. I can use exactly the same data that I have from calculating the mean energy. So it comes for free. The manuscript on this is on preparation, the main author is Anton. But this is a rough estimate of the runtime as a function of number of qubits, considering specifically what we consider a quantum advantage regime, something which more than 60 qubits, okay? Now, and here I compare two curves. The first one is a standard measurement, of course, using adaptive QE, but without informationally complete data. And this one is, this one is without informationally complete data, and this is our method with VQE SCF and with informationally complete data. I'm doing a number of assumptions, and I'm happy to discuss them later on, but they are not far. Many of these are really taken from the results that Antonio has been presented before for PEC, so for probabilistic error cancellation. We take many of the values of the noise in the experiments that they use, and so on and so forth. But I'm happy to. The main one here is really a measurement cost reduction for commutator evaluation. And again, we can discuss it later. I'm happy to discuss more in the answers. So this addresses these 2 points. Hilbert space is big, qubits are a scarce resource. How about the noise? How can we, again, exploit the advantage of informationally complete data to mitigate the noise? We are talking about winning the noise battle, winning the noise battle before reaching fault tolerance. Again, this is, everyone wants to go in that direction, but it's in the shorter term. The results are in this preprint. The idea, again, is from Guille, and I'm presenting a virtual linear map algorithm, or VILMA, for post-processing the data and cancelling the noise. Okay? And you find, Daniel Cavalcanti has coordinated the research. So the goal is to estimate physical properties, not of the state, but of a modified state, after you apply a map, but virtually. Okay? The key features are, first of all, because we use informationally complete measurements, it does not require full state tomography. The expected values are not of the state, but of the image of the state after the transformation. So in this sense, it's more general than classical shadows. And of course, we want to use it to invert the noise channel in post-processing. Clearly, there is a price to pay. When we do so, this increases the variance, but it turns out that this is still better than state-of-the-art noise mitigation schemes. How does this work? Okay. So the key reason why this works is that we consider a number of classes of maps which are circuit-like that can be treated in terms of using tensor networks. Therefore, they are efficiently computable. And there's a large number of them. And we are able to show that we are able in this way to treat up to hundreds of qubits and tens of layers. In general, you have to restrict, or you have to impose classical efficiency in the map lambda. And I will show now one example of what you can do. You can do many things, but one example is noise mitigation, assuming that you have beforehand characterized the noise, okay? So you or an experimentalist, someone else, so you have a model of the map, the CPTP map which contains the noise. What you will do is that you measure with informationally complete data, and then you do what is an unphysical, and actually Antonio mentioned it, it's unphysical because I'm inverting the noise. I'm inverting a CPTP channel, which is not a CPTP channel, so it's not physical, right? But I'm doing it in post-processing. How does it work? Instead of an ideal circuit, what you want to implement, you have a physical circuit which contains noise. Now, this figure is misleading because actually you would have also crosstalk, and so you may have a gate somehow, or a channel which contains all the 4. But it's for simplicity and graphically that we use this notation. And then you could imagine that if you add to this the inverse, again is unphysical, followed by the unitary you want to obtain, you will obtain the ideal circuit. This is just by definition. But of course, we do not implement this. We measure here, and we post-process by simulating this. Of course, you will say, I mean, this is large. I mean, if you can simulate classically on a classical computer this, why can't you do it here? I mean, this is twice as large, right? What's the trick here? The trick is that if this noise is sufficiently small, the combination of this is close to identity, okay, as you will see it here, because, well, by definition, right? So the combination of these two is close to identity, so for small values of noise, you can write this in a way that is classically implementable as a function of tensor network. So you have actually an expansion, okay? So this obviously does not work if the noise is very large, but we can prove that it works for bounds that are achievable, okay? And I will show you some results on how it works in the next slide. So this is all in post-processing. What we obtain is that the reduction with respect to PEC, which is really one of the most successful noise mitigation strategy, is exponential in the error reduction. We don't obtain a non-exponential curve, but the exponential error reduction. I will show it in the next slide. So this is the analysis. So here we have overhead as a function of number of qubits. Overhead is defined as the ratio between the number of measurement runs which are needed to achieve a given precision with a certain noise mitigation strategy, whether it's Vilma or PEC, and the number of shots without noise mitigation. So these dots here are the dots related to PEC, and these are related to the simulation using Vilma, so noise cancellation using Vilma for several different molecules. And what we obtain analytically is that roughly this coefficient, just I remind this from the Antonio's talk, the overhead is gamma bar to the power of nd, where n is the number of qubit and d is the circuit depth. So this gamma of Vilma is roughly the square root of the gamma of PEC, okay? Which obviously lead to an increase. What is important is that being this in post-processing, actually it can be combined with PEC. So actually it can lead to either further advantage. So this closes or addresses the point of noise, not completely, but we think that this is a very valuable strategy. And this brings me back to my claim. I think that we are not so far from proving in near-term quantum computers practical quantum advantage. I think and what I mean here with not so far is as the experimental is reduced of maybe one order of magnitude, we could be already in the range of what is achievable. Now, I'm concluding. How many people are still skeptics? So my claim is we can achieve quantum advantage for useful, for example, chemistry or materials, quantum computation with near-term devices. So if you're skeptic about this, please raise your hand. Don't be shy. Okay, I see only 2 people. This is impossible. I think some people are unable to do this. Okay, you will say, there is another one. Not anymore. Okay, this is of course, I don't believe you people. I know that among the audience there are people who instead don't think so. Let me show you this, and I will conclude. For those of you who don't believe, this is a picture of the Apollo guidance system with the DS key. The Apollo guidance system, which took men to moon and back, had a RAM of 4 kilobytes and a hard disk of 32 kilobytes, and 4 kilobytes is not sufficient to store even a 5-qubit density matrix in double precision, okay? So what I'm saying is that this very limited device, like the quantum computers we have now, together with this code, this is Margaret Hamilton, who was the chief of the team of software engineers who programmed the Apollo guidance computer, managed to do something epic. She recently, I saw an interview from her, she recently said software eventually unnecessarily gained the same respect of any other discipline. And I want to conclude with a quote from her that I like very much. She said, "Looking back, we were the luckiest people in the world. There was no choice but to be pioneers, no time to be beginners." Thank you very much.
Thank you, Sabrina, very much. So time for questions.
Yeah, thank you. First, I want to comment on the quantum advantage. So in BeyondC, I noticed the BeyondC conference, we actually all promised to do quantum advantage.
Okay, so that's why there was
a bit of a biased audience here.
Yes.
But I also have a question. So in some of the slides, I was confused about statistical error and bias error. So, for example, you compared in the very beginning to the chemical precision
Yeah.
And I thought some of the graphs were actually statistical errors and some were
Let me just go here. Is it this one? This one is the one in which I consider the bias.
I think it was the earlier one, but in general, chemical precision means, right, the deviation from the true ground state, right?
Yes.
And in your methods, what you're reducing is the statistical error, right?
Yeah, and we are reducing the statistical error towards a value that is... Chemical precision is really a number that chemists use in order to give a boundary of where you want to go, okay? And this is exactly... and this is what we are reducing in the statistical error to go as close as possible to this. The variance associated... So this line that you see here is then the variance of the estimated mean that we obtain.
Yeah,
okay?
That's
so
my confusion, because
yes.
the variance can also be zero and you still are away from the true ground state, right?
Yes, but this is not zero, okay? So
yes.
This is the statistical error as defined in the previous slide at the very beginning, right? And what we obtain is we obtain an estimation of the mean energy from which we calculate, of course, the error, so the distance with respect to the exact ground state in this case, because it's a small molecule, so we can calculate the exact ground state and estimate it. And then we can also calculate the variance of our estimation, okay? Because, again, we can use it with the same data, and the variance of our estimation is given by this small line that you hardly resolve, okay? While this one is the error with respect to the exact ground state, that is what you can diagonalize, okay?
All right.
I'd like to ask about the lithium hydride calculation. Does that have error?
Sorry?
Does it have error?
That is a good point. So, no, in that plot, we do not model the noise, and what we instead do is that we assume to use the noise mitigation of Vilma to cancel the noise. So in that is state vector simulation, okay?
So no error at all? No measurement error?
No, the measurement error comes here.
Why is qubit adapt?
I will explain where is the error. The calculation of the error is here. It's in the scaling. So let me, sorry, this is unfeasible, but I don't want to go there. So in the runtime, we consider instead what the error would do. So maybe it's easier if I go here, because it takes forever. So the effect of the error is calculated in the scaling here. Well, I can actually show you. This other is the same. As a matter of fact, this is with including Vilma. So here we consider errors. We consider the overhead. That is, in particular, we consider an overhead for C0 errors of the order of 10 to minus 4, a coherence time with the noise of 12 microseconds. So in this scaling, we do an analysis which includes the values of the errors for the same technique that I showed you before. Okay, so it is not the numerical experiment per se, but it is the scaling.
What about the plot you showed with qubit adapt and the optimization of the orbitals?
Yes.
That seems to be very different than what we find for lithium hydride. So I was just wondering if you have something we don't have in our simulation.
Okay, so I think it was this one.
Yeah.
Yes. Mm-hmm. Yes. So here the whole point is that we use CAS. Let me explain again. So this plot here, this difference, this delta E, is the difference, what we call this error delta E, is the difference of the energy that we estimate with respect to the energy of the CAS-SCF. So we calculate classically, with quantum chemistry, not VQE methods, CAS-SCF energy, and this is the difference with respect to CAS-SCF. But here, in the qubit adapt VQE, there is not the SCF implemented, it's only a CAS VQE. So by definition, you cannot get a value of energy which is lower, okay, than the one of the CAS.
So it's not telling you anything about the deviation from the exact energy?
No, it is benchmarked with the, okay, obviously, okay, I repeat. So the larger is the number of basis sets you consider, or the more accurate is the method that you use, the smaller will be the energy that you will reach. Now, if you use no CAS at all, you will be bounded by this high value of the energy. If you will use a CAS method, you will not go below this. So actually you converged in this method that is here. This shows perfect adaptive QE because you immediately converge to what is the minimum of CAS. Okay? But if you want to go below that value, you have to compare with the value of CAS SEF, which is including the rotation of the orbitals at each step. So in CAS SEF, you don't just use the active space, but you optimize the orbitals on the go. So you keep rotating and finding always better basis set, better orbitals. And this allows you to go to a value of the ground state, which is lower with respect to any value that you would obtain with CAS, and also, of course, with respect to any value that you would obtain without CAS and without active space per se.
But what would be the error from the exact solution here?
We don't do here. The exact solution would be much below, because neither CAS SEF, not CAS, nor without CAS, are in this case would be approaching the exact value.
Okay, the reason I'm asking is that I'm looking at our paper
Yes.
for qubit adapt, and with fewer than 5 CNOTs. Sorry. Okay, I see. So you are in the. Okay, I agree with you. All right, thank you.
Sorry. Okay.
All right, so maybe one more question and then.
Yeah, thanks for a very nice talk. I'm wondering about these adaptive methods you use. So what is the statistical method to compute the update?
Yeah.
And how does the computational overhead look like?
Yes,
So what is computational time to compute the update compared to the time of a measurement?
Yes, this is a very good point. So, first of all, we use to adapt. We just use a gradient descent. So it's a very simple. Our first, try for adapting the measurement strategy was just use gradient descent, and it is implemented very simply. But actually, it does depend very much on the type of optimizer you choose to find the best step, and that's why we observe even a better value of the scaling if we improve the method that we use. However, when it comes to the overhead, remember that we are not throwing away the first measurement results. So if you don't do anything, you would still remain at the initial value, right? So the point here is that this is done on the go. So, I mean, we keep going lower just by, say that in the first plot, we just do 1,000 measurement shots, and we have something very bad. But then we are not throwing them away. We use another 1,000, and we use them, both of them, and so on and so forth and so forth. So if you would, what we are just saying is that if you want to do, or if you need to do 10,000 times, 10,000 measurement shots, instead of just having 10,000 measurement shots, you can divide them in chunks and keep optimizing. Okay? But so in this sense, there is no overhead with respect to what you would like to do naturally. Okay? So you fix, say, I want to do it with 100,000 measurement shots, fine. Divide it in chunks, and instead of doing it naturally, just do it in this manner.
Okay, thank you.
Yes, thanks.
All right, so thank you, Sabrina, very much for the wonderful talk.
Thank you.